we will study what is called Blasius solution, which is solution for boundary layer on a flat plate with uniform flow at infinity. Uh, uh, so, uh, can you see this?
Yes, sir.
Okay, and is my voice clear? Okay. So today we will look at this. Now for uniform flow, we know on a flat plate, capital U of x is given as constant, which is the uniform flow density. Because in uniform flow, the potential flow, the streamlines are like this, are straight. And so we replace any one of these by a flat plate. And so this is uniform flow past a flat plate, and capital U of x is just the constant value u0. So because of this, du by dx is 0, and therefore the boundary layer equations are continuity equation and so these are the boundary layer equations. And along with these, we have the boundary condition at y is equal to 0. U and v are both 0. And as y tends to infinity, small u is equal to capital U. Now, the Blasius solution consists of converting the PDE to an ODE. Now, it is not always possible, as we have seen, to be able to do this exercise, but for these equations, we can do it. And what we do is we cast the equation in terms of the stream function psi. So instead of calling it, writing the equation in terms of u and v, we put it in terms of a single variable. Now, are we allowed to do this? Can we write the equations in terms of psi? Will a stream function exist for this flow? And if so, what cause, why? Or if not, why not? The flow is rotational. It is not irrotational. So will a stream function exist for this flow? Any answers?
I think yes, it will
Why?
exist.
What is
Uh,
the,
so
does
because
not,
so for 2D flow and rotational flow, stream
this
function
is not irrotational. Flow is rotational.
oh,
If it is irrotational, then a stream function, then a stream potential or velocity potential phi exists. Only phi will not exist in the boundary layer because the flow is not potential flow. What is the condition for existence of a stream function?
uh,
And this will be because the flow is incompressible. When we had done incompressible flows, we had defined, in fact, we said if there are only two terms in the continuity equation, you can define a stream function. So here, if I'm talking of a stream function, u is equal to partial psi by partial y, V is equal to minus partial psi by partial x. So we will put in these equations. This will be substituted in this equation. So we will get a third order equation for psi. So basically we will U and V will not exist. Continuity equation is automatically satisfied by definition of psi, and the second equation we will get a third order equation in psi. Now let us look at this term nu d to u by dy. This is also called the diffusion term. And as we have seen in Stokes' first problem, when we have problems like this, the diffusion length scale, this is given by square root of nu t, and in this case, t is equal to x upon u. So the diffusion length scale associated in the y direction, this will be given by square root of nu x upon u. And this we also know that physically, we have done this order of magnitude analysis. Y scales with delta, and delta we have seen is of order of nu x upon u. Now the distribution of velocity at any station x in the y direction is determined by the viscous diffusion, because this is what viscosity does in the y direction. In direction, the velocity distribution is smeared by viscosity. And the convection of vorticity is by the vorticity in the flow is being distributed in the x direction by the upstream flow, by the flow which is coming. So delta of x which we have, we expect it to be a function of x. It will, and what we do is if we try to define a variable eta which is non-dimensional y, this will be equal to, we write it in terms of y divided by delta of x, and based on our what we have done, the order of magnitude for delta, this becomes equal to capital U by nu x, this is all under root, times y. So we define this will is equal to capital U by nu x to the power of half times y. Now U is equal to partial psi by partial y. V is equal to minus partial psi by partial x. So we are in some sense trying to get the value of the similarity variables, the scaling of that by writing eta in this form. And then of course we have to feed it in the equation. If we get an ODE in eta and all x's cancel out, that means we have done the right thing. Now, so we have u is equal to like this. So now v which we have seen its order of magnitude is equal to delta times u upon x. Du by dy is equal to dv by dy is equal to du by dx. And so this will go like x to the power of minus half. Delta goes like x to the power of half, and there is a x there at the denominator. So this will go like x to the power of minus half. And this is what we have as also times function of eta. Now, the stream function psi, if I try to look at the scaling from this equation, is something like integral v dx. So based on this, we try psi is equal to, now v is delta u by x, and when I integrate it with x, so there is a x to the power of minus half dx. That will give me x to the power of half. So we try psi is equal to nu times capital U times x times a function of eta. So this is, in some sense, we would have got these from the equation, but we are starting by putting them in this way. So what we are doing is, we will put eta is equal to, this is the form for eta we will take, and for psi we will take this, and we substitute in the momentum equation. Now eta, let me write it again, for is equal to capital U upon nu x to the power of times y. So I'm going to need the derivatives of these. Partial eta by partial y will be equal to nothing but capital U upon nu x to the power of half. And partial eta by partial x, this will be equal to u upon nu to the power of half times there is a y, and then I have to take x to the power of minus half. So minus half times x to the power of minus 3 by 2. And this becomes equal to u upon nu to the power of half times y. I'm going to replace y by eta times nu x upon u to the power of half times minus half times x to the power of minus 3 by 2. So I'm replacing y by eta and x. And when I do this, this becomes equal to minus half will come from here. And then we will have eta divided by x. Because this u and nu will cancel out. And we have x to the power of half, x to the power of minus 3 by 2. It becomes x to the power of minus 1. So therefore, this becomes equal to minus half eta upon x. This is partial eta by partial x. Now psi, as we have seen, we are trying to put the form nu times capital U times x times f of eta. Now u is partial psi by partial y. So this will become equal to nu u x times f prime of eta times d eta by dy, and d eta by dy is equal to u upon nu x to the power half. So this, if you look at this, now nu to the power half will cancel out, and then x and x will cancel out, and we have equal to, what we can write is, and there are two u, so this is equal to capital U times f prime. And this we can also write in a non-dimensional form. Small u upon capital U is equal to f prime of eta. Now similarly, we need to find the equation for v. V is equal to minus partial psi by partial x, and this becomes equal to, now let's differentiate this. So first term will become square root of nu u times square root of x. So square root of x differential will become half times x to the power of minus half, and we have this f of eta. And then we have the second term, nu u of x times f prime times partial eta by partial x, which is minus eta upon 2x. So this, when we work it out, we get half. Now, nu u upon root of x, that is common, so we take that outside. So we write it as nu times u upon x to the power of half times, now we get the term eta f prime minus f. There's a minus sign outside which I forgot, so I take that inside. So then it becomes eta times f prime minus f. I had forgotten this minus sign, so please put this in. So that is what v becomes. So u is equal to capital U f prime of eta, and v is equal to half u by x to the power of half eta f prime minus f. Again, you know, this is just derivation. Now we need to find u du by dx. So we write partial u by partial x. We will need partial u by partial x is equal to capital U times f prime. So derivative of f prime is f double prime times partial eta by partial x. What is partial eta? Minus half eta by x. So times minus half eta upon x. So this becomes equal to minus 1 by 2 capital U f double prime eta divided by x. Partial u by partial y. We need the second derivative actually. So this is equal to capital U times, there is f prime, so it becomes f double prime times partial eta by partial y. This partial eta by partial y, u by nu x, so times capital U upon nu x to the power half. And we take a second derivative because in the right hand side we have the second derivative d2u by dy square. This will become capital U times f triple prime times, we multiply by the same thing, square root of u by nu x. So this becomes u by nu x to the power 1. This is partial u by partial y. And we also need u partial u by partial x. This will become equal to u is equal to capital U times f prime, and partial u by partial x will be equal to capital U f double prime times minus eta upon 2x. So this becomes equal to minus half times or minus 1 over 2x eta u square f prime f double prime. This is u du by dx, and we also need v du by dy. We had already derived in earlier. What was v? Or v was done here. V was equal to this thing. So v will become half nu u upon x to the power of half eta f prime minus f times capital U f double prime u by nu x to the power half. So this is v du by dy. And so this, when I simplify, this becomes equal to half u square upon x times eta f prime f double prime minus f double prime. And then we have nu d2u by dy square. This becomes equal to nu capital U f triple prime u upon nu x, and this becomes equal to u square f triple prime upon x. So now when I add u du by dx plus v du by dy, these two terms will cancel out, and what we get is the equation becomes equal to, so this implies finally we put all this in. Boundary layer equation is f triple prime with boundary conditions and the other boundary condition f of 0 is equal to 0. This comes from v is equal to 0 at theta is equal to 0 and f prime infinity is equal to 1. So this is called Blasius equation. That is f triple prime plus f double prime by 2 is equal to 0 with above boundary conditions. So, and now there is no closed form solution. So instead of solving the PDE, we can now solve ODE, and this can be done. So we look at f prime as a function of eta in the solution. It looks like something which matches, and around eta is equal to 5, this curved part or flat part of the plate has come. Now, from the solution, basically, why do we need to find this f prime is to calculate the shear stress. Shear stress is equal to mu du by dy at y is equal to 0. So this will be equal to mu times u du by dy is f double prime 0 u by nu x to the power half. And this, if I revert, this becomes equal to rho u square, because what I do is this nu, I mu and mu is equal to nu by rho. Nu is equal to, sorry, mu by rho. So that's why this cancels out and we get a rho u square times nu upon ux to the power of half times f double prime 0. And this we know is nothing but 1 over Reynolds number. Now f double prime 0 is equal to 0.332 from numerical solution. So that means shear stress at the wall is equal to rho u square so shear wall in the stress, if we calculate it out, this becomes equal to divided by Rex, where Rex is equal to ux upon mu. So that means what we find is the shear stress is proportional to 1 over root x. So if this is the wall, you start the flow at y is equal to 0. when this becomes equal to, so this is the shear stress at the wall, which is proportional to, sorry, this point I do not want to make it. Tau wall becomes equal to 1 over root x. Now, how do we find this 0.33? Any idea? How do we find this 0.33? And this comes from slope of this at y is equal to 0 or eta is equal to 0 is f double prime of 0. So that is where we get, and this we get from numerical result. From the numerical solution we get, that means we look at the slope at the origin and we get this is equal to this. Now, shear stress we have seen is proportional to 1 over root x, but the drag force on the plate, this will be given by integral tau wall dx going from 0 to L, and this is a flow on one side, and this is equal to 2 times 0 to L tau w dx, a flow on both sides. And the drag force, let's assume that the flow is on both sides. So drag force becomes equal to 2 times integral 0 to L tau wall, and this becomes equal to 1.33 rho u square L times Reynolds number to the power of minus half. So now in REL there is a square root of L, there is a L here. So drag is proportional to square root of L. Whereas the shear stress tau was proportional to 1 over root x, but the integrated drag force is proportional to root L. And these are some of the things of the Blasius solution. If you want to integrate this, you can easily integrate this equation using MATLAB. You can try it out. You'll have to make it as a set of 3 first order equations. Let's say f prime of 0 is equal to p, f double prime, you call it as q, and f triple prime will be r, or so dq by d eta plus f double prime, whatever they are, you'll be able to get this. So this is the Blasius solution for a flat plate. Are there any questions? I know I've been sort of going on in a monologue today and just going, but do you have any questions?
No, sir.
No? ठीक है, ये हो जाएगा. Now, what I'm going to do is, for the homework, you have to look at the case where capital Ux is equal to a times x to the power of m. So the flat plate is a case when m is equal to 0. And this, let me just, this represents flow past a wedge. That means this is what we call as a, so this, in this flow, when capital Ux is equal to ax to the power of m, flow will come in from infinity like this, and it represents flow flowing past a edge. And if the wedge angle is beta, this is related to m. I don't exactly remember. You can again check it up. I think it is m plus 1 by 2 or something like that. Or beta is related to the angle beta is a direct function of m. And here, following above steps, where you keep again capital U, you keep as ax to the power of m. So now, even when you non-dimensionalize, this u will become x to the power of m. So therefore, this will become x to the power of m plus 1. And eta will be, again, when you write eta, this u will become x to the power of m. So x to the power of m minus 1 by 2 will come here when you work it out. And this, I'll make this problem, put this up hopefully today. And then following the above steps, you can get set of ODEs, exactly defining it in the same way. And these ODEs are called the Faulkner scan equations. This is what we will be doing, but we will, so again, the solution of the ODEs we are not doing, but we can reduce these boundary layer equations to an ODE. Now, for a general U of x, similarity solution may not exist. And because these equations are nonlinear, you can't even say that we will sum up any general U of x in a polynomial series of x, if that exists, and then add up, find each solution, add up all the solutions, because linearity is not going to work here. So, and it is here that for any general x, so for example, if I talk of flow past a cylinder, so I will not get U of x will not be of the form a times x to the power of m. In fact, it will take some sine or cosine distribution. So there the similarity solution may not exist. And what do you do? And in such cases, at least one way of solving it is these equations is using the approximate method by solving the momentum integral equation. Do you all recall what is momentum integral equation? Do you recall what is the meaning of momentum? Or have we seen this before? Momentum integral equation.
Yes, I mean integral equation of
We saw
neighboring.
it in the last class. In the last class, we derived this equation. And this was, as far as the equation goes, this equation looks like this. So, and these sort of approximate methods, once again, became popular when computers were not there, CFD was not so advanced. Because you use these equations, you find some sort of a way of solving these equations. But in today, if I have to solve the boundary layer equations, I will just go for solving the partial differential equations themselves. But the reason why I'm doing this is you will see that we will see a lot of aspects of physics in these problems when we use the approximate method. Now, in the above equation, theta is equal to what we have called as the momentum thickness, and this was integral from 0 to delta small u upon capital U into 1 minus small u upon capital U dy, and delta star was the displacement thickness, and this was given by integral from 0 to delta 1 minus small u upon capital U dy. And let's look at the approximate method. What the approximate method says. First, we assume small u upon capital U is equal to f of eta, and eta is equal to pi by delta of x. So we are assuming a similarity type of profile. So we assume a velocity profile in the boundary layer. So if we have a picture like this, we are assuming the shape of this profile. Now, what are the conditions what we expect? So this basically this is being given by f, because it's capital U times f of eta. That is the velocity profile. Now, f we expect it to be a smooth function. We don't expect the velocity profile to be discontinuous or anything, which rises monotonically from eta is equal to 0 to eta is equal to 1. Eta is equal to 0, this is the wall. Eta is equal to 1 is nothing but when y is equal to delta. So this is equal to, this is the edge of the boundary layer. So we will assume this function, uh, assume that there is some profile which is given by this. And what type of f of eta can we assume? So we can make different approximations. And one very common assumption which was made was that we assume it to be a polynomial in eta. That means we assume f of eta is equal to a0 plus a1 eta plus a2 eta square plus a3 eta cube, and we can truncate it at any level. Now, when we assume like this is the velocity profile. In this assumption, at least at this stage, a0, a1, ai's, they are unknowns. And to find these, we have to use the boundary condition on the velocity. Now, let's try to draw a cartoon of this. That this is the surface, and I'm deliberately now drawing a curvilinear coordinate system because, and y at any instant will be perpendicular. So this is y, and if this is the boundary layer, eta is equal to 1 is the edge of boundary layer. This is total delta, and so eta is 0 here, and eta is 1 at the edge of the boundary layer. Now, what are the boundary conditions we have on f? F is nothing but, keep in mind, small u upon capital U. Now, the boundary conditions will come on eta equal to 0 and eta is equal to 1. So now, what can you say is the value of f What is F at eta is equal to 0?
0.
Why? Because the velocity is 0. We just feed it in here, small u is 0. So F of 0 is 0. And what is F of 1? What do you expect F at eta is equal to 1?
Capital U.
No, so what is F?
U. Small u upon capital U.
Yeah, so then what will be the value of F? If small u is equal to capital U, what
Oh,
will
so
be F?
this will be, it will be 1, 1.
Does everybody understand this?
Yes, sir.
See, now these two conditions are something which will be satisfied for all boundary layers. That at y is equal to 0, velocity has to be 0. At y is equal to 1, or eta, sorry, not y. Eta is equal to 0, velocity is 0. At eta is equal to 1, velocity f has to be equal to, velocity will be capital U, which means f of 1 is equal to 1. So these two boundary conditions are what we write as essential boundary conditions. Any profile, and the reason for this is when you use different type of profiles, you will have to use many boundary conditions. But these two boundary conditions have to be satisfied. So that is why we call them the essential boundary conditions. They have to be satisfied. So first, satisfy the essential boundary conditions. But suppose if we have chosen, if f we have chosen as a0 plus a1 eta plus a2 eta square plus a3 eta cube. Suppose we have chosen it like this. Now we have four constants a0 to a3 and we have two boundary conditions. These two we have satisfied. So we will need two more boundary conditions. And how do we get them?
By smoothness condition.
Okay. So these will come at eta is equal to 0 and eta is equal to 1. Eta is equal to 1 will give us what we call the smoothness condition. So that means this will tell us this one. So eta is equal to 1, we will get, that means at eta is equal to 1, du by dy, d2u by dy square, and all higher derivatives must be equal to 0. This is the smoothness condition. But I have a basic problem with this. If I use all the smoothness boundary conditions, then all my boundary conditions will be there for all type of boundary layers, irrespective of what is capital U of x. If we use essential plus smoothness boundary conditions, the profile will not depend on capital U, because we have nowhere used the value of capital U. We have just said it must be 1. So if we want to do this, we need to explore boundary conditions on eta is equal to 0. So that means, do we know? So what we are saying, of course, is the smoothness boundary conditions imply du by dy at eta is equal to 1 is 0, d2u by dy square at eta is equal to 1 is 0, and so on. And du by dy will lead to df by d eta at 1 is 0. This will lead to d2f by d eta square at 1 is equal to 0 and so on. But now at y is equal to 0, let me look at it. At y is equal to 0, what is partial u by partial y? This will be equal to partial by partial y. Small u is nothing but capital U times f of eta. So this will become equal to capital U times partial f by partial y. So capital U times df by d eta times partial eta by partial y. So this will be equal to u times f prime upon delta. Now du by dy at y is equal to 0 is not available as a boundary condition. Why? Because this is nothing but shear stress upon the wall divided by mu. And this is what we are trying to solve for. In fact, this even comes in our equation. If you look at the equation has a term containing tau. Where is it? Okay, sorry.
Yes, sir.
The equation has a term containing tau wall. So the first derivative of u at y is equal to 0 is not available. What about is that known from from the problem? What is d2u by dy square at y is equal to 0? And this is the point I wanted you to understand this, and that's why I am doing this. Uh, so what we have here is, let's look at and to get this, we look at the x momentum equation. This equation is valid for y is equal to 0 also. It is valid at the plate as well as in the fluid. Now, what is the x momentum equation? U du by dx plus v du by dy is equal to capital U du by dx plus nu d2u by dy square. Okay. du. Okay. See, actually, in fact, I think I've goofed up slightly. Let me just see. Du by dy. Yeah, okay. No, that's fine. Okay. So now, okay. Now what do we do? What is u at y is equal to 0?
0.
This is 0 for all x. We are applying this boundary condition. Apply at y is equal to 0. So u is 0. Now, what about v at y is equal to 0?
So it depend on the wall. I mean,
It depends on the wall, and this will be 0. So u at y is equal to 0 is 0, and this will be 0 for a non-porous wall. Okay. So irrespective of everything, we will get the left-hand side will become 0 at the wall if it is a non-porous wall. Okay.
yes.
Now, so what we get from here is at the wall, d2u by dy square is equal to minus u du by dx into 1 over nu. Okay. And this means, so this tells us this is d2u by dy square and y is equal to 0 is equal to this. And this is nothing but, so d2u by dy square, u is equal to capital U times f of eta. And so du by dy, we have worked this out, was capital U times f prime times d eta by dy was 1 over delta, and d2u by dy square, this will become equal to capital U f double prime upon delta square. So what I get from here is I feed this here. So capital U f double prime 0 upon delta square is equal to minus u du by dx to 1 over nu. And from here, what I get is f double prime 0 will be equal to minus delta square upon nu into du by dx. And this is the boundary condition we get. F prime of 0 cannot be found. But f double prime of 0 turns out to be equal to minus delta square upon nu du by dx. And this we can use as a boundary condition. Is this clear?
Yes, sir. Sir, I have a doubt.
Yes.
Sir, if there is a, second order polynomial equation or third
Yes.
order,
Yes.
then which boundary conditions
Yes.
we use first? Smoothness or
Yes. It is the same doubt which you have, even I have. So now what we are saying is, if there are two boundary conditions needed, then we will use the essential boundary conditions. Okay, that is very clear.
yes, sir.
If we need three, then which one do we use? Do we use f double prime 0 or do we use f prime of 1? It should be one of these,
Yes, sir.
isn't it? And the answer to that, I think we leave it up to the, uh, I would say, unless if f double prime of 0 makes the third order polynomial as a second one, then I will not use it. But otherwise, I will first use f double prime 0. Why? Because it incorporates the value of capital U of x in the solution. So normally the third and fourth which we use are f double prime 0 and f prime 1 in whichever order. If f double prime 0 converts it back to a linear polynomial, then I will use f prime 1. Otherwise, I will use f double prime 0. And if there are four to be needed, then it is clear to me I use them. Now, after this, can I find f triple prime 0? Ajab, now, let me just finish this and then I'll pose a question to you, whatever you want. Can we choose f triple prime 0? How do we find that?
So we may differentiate
We will
x.
differentiate the x momentum equation. So we have u du by dx plus v du by dy is equal to capital U du by dx plus nu d2u by dy square. So we differentiate this with respect to y. So you can do it, and this will give you. So now d by dy of capital U du by dx will be 0 because everything only depends on x. Okay, and what you from here you can get f triple prime 0, and you can differentiate again, get the fourth derivative, and keep on doing this. But these are basically the way we have done this. Of course, this will be straightforward to find if u and v are 0 at y is equal to 0. And what happens is, what you will be able to show is, if u is equal to 0 and v is equal to 0 at y is equal to 0, then f triple prime of 0 will be 0, f fourth, and all these will keep on giving us zeros. And this you can show. I'll not show it. You can try it at home. I'll ask you to try it in the exam. Okay.
Yes, sir.
Now,